Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman, and I'm the Marketing Director here at the Academy. Today's webinar is titled Untangling the Role of AI in Water from Promise to Practice. Our Executive Director, Dr. Daniel Uther, will serve as a moderator and will introduce our speaker today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. Before we get started, Dr. Uther would like to say a few words. Dan, how are you doing?
Good afternoon, Marissa. Great to see you. I'd like to offer a welcome to everyone who's joining our webinar today. This is the last in a series of webinars organized by the American Academy of Environmental Engineers and Scientists on the broad subject of artificial intelligence. We've learned a lot over 4 webinars, from how a teenager views the technology and its use in schools, to how researchers and practitioners use the technology to advance knowledge and to lead projects for clients. Today, we are joined by Professor Branko Kirkez from the University of Michigan to speak with us about untangling the role of AI in water from promise to practice. Before we get started with our speaker, I want to pause and take a moment to offer thanks to the patrons of the Academy. Patrons are firms and utilities, including those whose logos are listed on our screen right now, who financially support the Academy. When you speak with folks from these organizations, please say thanks for their support of Academy programming. It is in part through their generosity that we're able to bring today's event to our members at no additional cost. If you have an interest joining the Academy as a patron, or if you or your organization has an interest in proposing or sponsoring a webinar, please reach out and let us know. Marissa and I are here to listen to your story and to help match your needs with available programming. And now on with today's webinar. As I mentioned earlier today, it's my privilege to introduce Dr. Branko Kirkez, the Arthur F. Thurnau Professor and Director of the Digital Water Lab at the University of Michigan. Dr. Kirkez is also the Chief Technical Officer at HiFi, where he leads research and development of sensing and AI technologies for urban water management. Branko earned his doctorate and his master's in civil and environmental engineering, as well as a master's in electrical and computer science from UC Berkeley. At Michigan, his research group is working to enable smart water systems which autonomously adapt themselves to changing conditions using real-time data and controls. His research projects have spanned wireless sensing of large mountain basins, real-time flood forecasting, robotics, and control algorithms for water systems. He's the founder of OpenStorm.org, an open source consortium dedicated to freely sharing hardware, software, and case studies on smart water systems. Dr. Kirkez is the recipient of the prestigious Career Award from the National Science Foundation, and in 2018, he was recognized as a Gilbreth Lecturer by the U.S. National Academy of Engineering for his contributions to smart water systems. As Branko delivers his presentation today, I remind you that I have the privilege of moderating a question and answer event at the end of the presentation. So it would be incredibly helpful if you would share your questions in the Q&A panel throughout the presentation, and I'll use those to direct today's moderated discussion. And now, with those instructions and introduction, Branko, my friend, the stage is yours. We're so excited to hear from you.
Awesome. Thank you so much for the intro. So hopefully my slides are changing. If not, you can let me know. Thanks for having me. I'm really looking forward to sort of engaging with you during this, like, I guess on the Eastern time zone lunchtime. And we'll take a few intermissions as we go throughout this. But basically what we're going to do today is just kind of address this head on and talk about this thing called AI. Probably, I feel like I'm getting a door knock. Have you heard about AI? I have, because my TV told me. So even unsolicited, we're being bombarded with these things that are basically telling us how the world's changing in front of us, whether we want to, listen to it or not. And it's very common now to go to, let's say, a water conference, or really any conference, and the keynotes to be primarily related to this kind of stuff. We're hearing, for example, that, AI is going to transform water management. And something that's being implied, it seems like, is that somehow present water management isn't smart. So somehow we need to make it smarter. So we need smart water, whatever that means. As I always tell people, I thought that was already a copyrighted term, so I don't know how we're using that, right? Or my favorite term, digital twins, right? Things that sound like something, but still unclear what it is. So if you're unclear, you probably arrive at the same conclusion as I do, which is this is probably what we're talking about, right? The point is, stuff is happening around us, and people are engaging with these tools. They're writing their essays, they're writing their reports. And it just kind of feels, for the lack of a better term, it feels sort of magical. There's something going on. And so this field, this term AI, artificial intelligence, has this habit of feeling, I don't know, like magic, right? And the thought for today was, sometimes this hype around it, even though it has these promises and some of these risks, sometimes the hype doesn't lend itself to like a level discussion because the terminology is confusing. And so what I wanted to do today during the session is sort of break it up into three parts. We'll do like mini intermissions. The first part to sort of just level set on terminology. So before we proceed, talk about applications and other kind of things. What are these terms? What does this mean? The second thing we're going to do is we're going to look at like what's possible now, cutting edge in what's possible, but what can we do right now? And then I think maybe the most interesting part at the end is discussing with all of you about what's coming up and both the squishy things and the tangible things that we're looking at as we're looking towards the future, both in terms of what's happening across the technological landscape as well as to our field broadly when we think about it as environmental and civil engineers and scientists. And so let's start with the terminology. So the good news is AI is not magic, even though it feels like it sometimes. It has its roots in just a bunch of math. And I'm putting up this timeline, this nifty timeline that I found over the last 50 years to tell people that if it's not magic, what it really is it's math that sort of started in the 1950s. Obviously, it's evolved since then. And it's finally found its home on some really big computers. And that's really what's kind of happened. So all of us as engineers and scientists, we already know how to do math. What's happening here is it's just really a bunch of math that's found its way on computers with some data. And I think sometimes it helps to just know the origin story. And so I'm going to take us back to the 1950s and just kind of see where the term came from. So there was kind of what ended up being a really famous conference in the history of computer science at Dartmouth University in the 50s by folks who would effectively become giants in the field of computer science eventually over time, who got together and said, hey, let's come up with this new concept. We're going to call it artificial intelligence. And I dug up went through the archives and dug up the invitation letter that was sent out. So you can see in June of 1956, we're proposing a 2-month, 10-man study. Okay, I'm underlining that because I think it's pretty funny. We're going to define this term, right? So when we talk about biases of AI, early on, whatever we call it, whoever came up with the concept, it was determined by some of these folks who kind of planted the seed. And they imagined during this 2-month workshop that there's going to be this field that we're going to call artificial intelligence. And they understood that computers could one day maybe serve lots of different applications. These could be things like, one day a computer might be your therapist. One day they might be so convincing when you talk to them, they might fall in love with them. I don't know how many of you have seen this movie. One day computers are going to be so good, they're going to, robots are going to watch our children so that we can go more on these 2-month retreats while we're positing about the future, right? And then one day we might even have completely unbiased police officers who are just going to take care of everything, and definitely they're not going to turn into the Terminator. So anyway, the point is it started off very, very broad, and they discussed this field and what would go into it. And what happens today is we're not really rooted in the terminology of this, and that leads to the confusion. So when we talk about AI, it was meant to do all those things, and one could argue it's getting close to doing those things. In our field, when we talk about environmental engineering, environmental sciences, civil engineering, what we're really oftentimes mostly talking about is actually a subset of AI that's called machine learning. Okay, so that's another term, and we'll break it down. So in our field, when we talk about machines, I think oftentimes it's pretty clear what we're talking about. We have a big project we want to build, the kind of things that like made me want to become an engineer. And we know that if you have a specific task you want to carry out, there is a machine for it. So when we have a giant pile of soil we need to move to build a brand new water project, we have the machine. Well, what happens when that giant pile of soil is actually not soil, but is data, right? That machine is not appropriate to it. And that's where we adopt the sort of classic terminology of what computer science calls their machines. When they refer to machines, they're actually talking about computers, right? And so this machine takes in data, it learns some sort of model to make some sort of predictions, and the learning part happens in the middle of this machine. And that's where the terminology comes in. So just to kind of level set on terminology, machine learning, subset of AI, takes data to produce a model, and it learns the parameters of the model. And there's a very simple way to sort of look at something like this. So I always like to put this equation up. Here's some math from the 1950s, maybe even before. I'm just kind of curious how many of you recognize this, right? Like that's what would be running on this machine. I think most people are oftentimes surprised when I tell them you've actually used this. This is the classic regression equation that sort of lives in Microsoft Excel. So when we talk about maybe predicting, X versus Y, let's, for example, say we have precipitation versus flooding, how much, this is just made up, but basically how much is it going to rain and how much is it going to flood? The model we're actually trying to learn is the kind of classic middle school model of fitting lines to data, right? Like I have a line, it has a slope, maybe it has an intercept. And if we learn this slope parameter, we can now predict flooding for some given precipitation. Again, a very simple kind of evocative model, but that's kind of what is going on here. So when we talk about machine learning, we're really talking about taking data, in this case, rainfall and observations of flooding, and we're learning that a parameter of that model, and that's what the machine does. So effectively, the machine is learning from this data and it's learning this parameter, and that's what this field is. And so basically, for most people, when I talk to them, especially those who are brand new to this kind of stuff, I always tell them you should pat yourself on the back already because you've effectively already done machine learning, which is part of AI, just simply by using Microsoft Excel, right? Obviously, that doesn't work for all applications, but it's not nearly as inaccessible as it seems, right? Because when we fitting X versus Y, and that relationship is maybe simple, Excel works. Sometimes we need some more fancy models, and this is where things like these newer models come in, like neural nets and XGBoost and all these. There's a world of models. The point is, when you have complex data, you may need a complex model, but all of those are just little circles inside this much bigger world of AI, ML. So again, as I said, there's complex models, there's simple models, and then there's things like this, right? So for those of us who teach, you've already experienced it, even if you think you haven't. Most things that you're reading now may or may not be AI generated. It's very likely that even if you don't use these tools, you've come across it or consumed it without knowing it. So for those of us teaching, we're getting submissions of very convincing kind of assignments, and we're still figuring out how to adopt our education to it. But it's very easy to write a complex task now into something like an LLM and get an answer that works fairly well. And so that's not Excel. That's not, anything that seems strange. That feels like magic. How does that work? And to sort of break that down a little bit and figure out how these components come together, I want us to also to maybe relive this collective trauma of taking a standardized test, maybe the SAT, and they don't have this anymore, but back in the day, they would have these things called analogies. You're supposed to look at an analogy and find something that's similar. So for example, a dog is to a puppy as a cat is to, and this is a very kind of simple, silly example, obviously kitten would go in there, right? That's the analogy. And so that's effectively what LLMs are doing. They're scanning the internet for lots of language, right? In this case, the data input that we're getting is not rainfall and runoff, it's language. And the language is taken from anywhere that there's language, books, PDFs, the internet. And, unlike water data, the internet is replete with cat and dog information. So it's very good. It's very easy to learn these kind of things because there are lots of data. But when you consume the entire internet, effectively what you're doing with this and all the text on the internet is you're taking language. Now, because you have a lot of complex data, you need a complex model, and usually they refer to these as large models. It's basically neural networks of interconnected components that might have, a billion parameters, a billion nodes and links in these models, unlike our Excel model that only had one parameter. And then you can produce language as the output. So language goes in, language goes out. Before we had rainfall and runoff come out. So essentially a large language model, that's where the term comes from, is just basically lots of language going into a large model that gives you a large language model. So again, like I know, just stepping through the terminology, wanted everybody just to see that once you train these models, you might be able to prompt them for things that are not just cat and dog, memes or, writing essays for college. You may be able to input, and I hear this from a lot of folks now, it's like, hey, I put in my engineering knowledge. Like, for example, a perfect stormwater management model ensures that, you fill in the blank and the model would predict something like this. And a lot of people claim like, well, they're still not there. They're hallucinating. It's called hallucinating when they produce results that maybe don't seem trustworthy. I don't know what they're talking about. To me, most of those look pretty good. But the point is that actually even these things that feel extremely complex live in the same exact bubble as our Excel model. And the reason why I bring this up is because there's a lot of hype around this, and people are using these terms interchangeably. LLMs, deep nets, ML, AI, and they use them interchangeably to a point where it creates confusion when it shouldn't. And it makes sense. The analogy I always give to people, Coca-Cola is part of the bubble of soft drinks, but yet still in the, in some parts of the country, we call all soda Coke. That's okay. That's how we're proceeding with all of this. It just makes it hard to be grounded in science, right? So when we want to talk about, scientifically about this, we do want to be careful about how we refer to individual models inside this bubble called machine learning, which is part of broader AI. And the thing I want to kind of point out to people is when we talk about AI for our field, oftentimes we're talking about this bubble over here, this machine learning component, and I'll take us through this as we go along. But the point is there is a world of models out there, and even these really special ones, the ones that reign supreme right now, like LLMs, deep neural nets, are just individual dots in this broader sphere. So again, just level setting for a second, even though it feels like magic, It's not necessarily magic. It's just, math that started in the 50s and co-evolved with computers to now allow us to just basically crunch a lot of data and make predictions. And it should not be nearly as intimidating as it feels sometimes because of, a lot of our training is not rooted in these methods because we know how to do math. I mean, take fluid dynamics. I don't think anybody would claim that that's any kind of trivial math compared to some of these things. Yet somehow this stuff seems inaccessible, and I'm personally convinced, or this is at least an opinion, that it's inaccessible because of the terminologies being thrown around willy-nilly. So that's just the start here. So what I'm going to do right now is just for fun, I'm just going to pause for 20 seconds to let everybody take a breath and think about how you've probably used ML before, you just didn't know it. So we've already all done it, and maybe think about like what these terms mean to you and all this other stuff. And I see Daniel turning on his camera to see maybe if he's got some input before we proceed.
Well, so here's the question, right? So like if I'm doing regression, I understand linear regression and curve linear. I understand interpolation, extrapolation. Do I force it through the origin? All that kind of stuff. Can you
Yep.
just give us a thumbnail of what's the equivalent of those when we're talking about some of this other stuff?
Um, well, I can take your question and say, rephrase it a little bit and say, you understand regression because you've drawn lines, you've spent time with that model. You've spent time with the model, you've drawn the lines, you even can see splines and curves. You can kind of get the intuition for it. Similarly, you've probably spent time with like water models. And I don't know, for stormwater engineers, it's SWIM. For maybe like folks that do treatment plants, it's a different kind of model. But all of us have intuition for the things that we've spent time with. So it is very accessible for these other models as well to sort of explore those things. So when I think about basic classification models like trees or support vector machines or all these other things, I can give you these kind of analogies, but the point is that spending oftentimes a marginal amount of time exploring these things will get you to that intuition. And what I'll do is I'll actually give you some examples as we move forward to show you maybe how some of that stuff manifests. But the point is that it's more accessible than it seems. Now, that's not to say that we can go into one of these LLMs that's got billion parameters and all of a sudden claim that we know how everything's working. Not everything is super easy to understand, especially when you go from, as you see with regression, you go from 1 dimension, 2 dimension, you can see it. Good luck in 3D, right? But you trust it at that point to hopefully be doing the same thing that it does in 1D, when you move to 10 dimensions, 20 dimensions, et cetera. So some things are more accessible than others, but the thing I guess I want to bring home is that it's still just a bunch of math running on computers. We're sort of in charge, and it's not nearly like you don't need to be a computer science master to be able to use these things at the least. Now, obviously, there's some really sophisticated people right now doing some really cool stuff out there. Not everybody needs to be developing the tools, but knowing how to use them is a separate kind of thing. And I guess what I'll tell people is compared to 5 years ago, let alone 10 years ago, the stuff is much more usable than used to be.
Awesome. Thank you.
Cool. Okay, so again, that's just starting off with terminology. So hopefully now when somebody says AI ML, you can tell them, hey, those things are just part of the same bubble, including ChatGPT. So let's take a look at, I want to show you a couple examples of how this stuff is maybe being used for the specific things that we're working on, like what's possible now, and then we'll discuss maybe where things could be going. And what I'll do is I'll step through 3 different applications. I'll start with a stormwater one, and then we'll do drinking water and some resource recovery stuff, some energy stuff, so we'll get there. Here's just an image from where we live in the Great Lakes region, so based in Ann Arbor, Michigan, and we contend both with flooding as well as nutrient runoffs and all these other things. And again, the classic approach, our field's approach to solving these problems is to bring out our machines. When you have flooding downstream, you dig a big hole or you make a basin to treat your water quality. Whatever you want to do, the point is we have these machines and we're putting those machines to use. When you don't have the kind of money that Chicago has to build a giant tunnel, like billions of dollars, maybe you build a lot of distributed assets in the case of stormwater. So maybe green infrastructure or nature-based solutions. And I wanted to show you like what happens when as we use our current machines, the question is, are we achieving our goals? And so I'll focus again on where we live, just as an example. Here's downtown Ann Arbor, even we flood, right? This is an image of near campus. And the city, like most cities across the United States, depending on what resources are available to them, is building lots of these solutions, distributed solutions throughout watersheds to contend with this. Some are gray, some are green, and we can have a discussion about, like how all this stuff works at scale. But what I'll do is I'll just focus on a conceptual example here of a 10 square mile watershed out I always tell people when you come to Ann Arbor, Costco's in the bottom left corner. That's my reference points because I'm not good with roads. But the point is, it rains over here, all that water flows downhill, and sometimes it causes issues across the watershed. And so maybe the city installs a pond, maybe they install a bioswale, some rain gardens, and they sprinkle them throughout, right? Because any given year you have a certain amount of budget, and then you go on and you implement these solutions. And sometimes what that feels like is, I always give people the Bob Ross analogy of, well, we're just doing all these good things. We're bringing out our machines, we're digging these holes, we're building this stuff, and how could that be a bad thing? Because if we install a basin and a pond here, we can put one here and put one here. And as Bob Ross always said, well, there's no mistakes, happy little accidents, whatever the analogy is for those of you late night Bob Ross watchers. Sometimes I feel like we actually don't have a large scale guide for this, and it seems like we're just sprinkling these solutions around, hoping that they work. And it bears to sort of like pause for a second and say, is that actually accomplishing it? And so in this conceptual example that I'll show you right here, we're going to look at just an example, a pond and a bioswale, for example, that were installed in 2 neighborhoods. And we do with these what we teach students to do in class. You have a site 1, site 2, you install these assets, and now we talk about the before and after performance. So what we're plotting here is, let's say, water levels in the neighborhood. This could be a stream erosion, could be flooding. And the point is, when it rains, water levels go up and down. And we always teach students that if you sort of spread out the hydrograph, you're accomplishing a really good thing. And that's true for those 2 neighborhoods. We're fixing neighborhood number 1, fixing neighborhood number 2. Those flows, though, go to a downstream location. And before you implemented these practices, you would get this kind of behavior. Site 1 and site 2 add up. But now if you're not careful about how you're tuning those sites in this context of the watershed, which very few people are, nobody's paying attention to that, those hydrograph peaks may be adding up in a way that they didn't before. In fact, before one arrived, then the other arrived, but because you sort of like edited the 2 neighborhoods, if you will, like in the landscape, now they're adding up downstream, whereas before they didn't, and you may end up getting worse behavior downstream. So again, I say may because we don't know what's going on. We're not measuring. We're not sure if these things are happening. So decade after decade, we keep piecemeal fixing our water systems. And we have this approach of like, well, how could that be bad? We're just doing good things all around. It's going to add up. But there's no guarantee. And there's a really good paper that came out of Claire Welty's group in Baltimore some years ago that basically showed that you can be much worse off if you're not paying attention to the system scale. So I guess, the word is, be very careful when you're bringing out our traditional machines, because you may be inadvertently causing bad things to happen, or maybe good things, but we don't know, again, because we're not measuring. And so if these machines are maybe limited, our approaches are limited, where else can we look to inspiration? And that's where we can look to other machines in other fields. And here I'm just taking like an example of a self-driving car. Self-driving car doesn't do the same thing every time as our infrastructure does. Water goes in, water goes out. The self-driving car has cameras, has devices that detect what's happening, and it does a different thing depending on weather conditions, or if a deer runs in front of you or whatever. The point is, it's adaptive. And some years ago, we sort of doodled down this picture of like, in collaboration with lots of folks, like what would a self-driving water system look like? And if you think about the cities of the future, maybe stormwater systems could be just like a self-driving car, embedded with sensors that are measuring real-time conditions, reporting what's going on in terms of water levels, flows, rainfall, soil moisture. All that's digested by something, and then you make a different decision to operate your infrastructure depending on that event. And we'll talk about how you could do that in real time in a second. Step 1 in that is to start measuring. As most of you know, we don't have a lot of measurements in the United States of water systems, especially watersheds. The USGS does a phenomenal job of operating about 8,000 stations, but with 3,000 counties, it's not a lot of data at all to begin kind of granular decisions. And that's where, to the point of the introduction, we've been working on open source tools to make this stuff accessible and affordable to measure water systems. So here's an example of one of our internet connected water level sensors. Think of your cell phone, where you just strip away the screen and all the stuff you don't need, and you just focus on the modem and the microprocessor. You connect a sensor to it. In this case, it's an ultrasonic sensor that measures distance to the water level. And then these are deployed and report data in real time to tell us what's happening in locations where we don't have measurements. And we have been for several years now just scaling these things out and working with communities on the ground to create this sort of blanket data infrastructures. Going back to machine learning, a machine can only learn if you have data, right? Like, how else are we going to get those parameters? And so this is just a snapshot of the current network, showing that even our little research group, some students downstairs, is able to deploy fairly large networks and maintain them. And part of that is several factors that go into it, and I'll show you some of those later. But it's a large network. And when you turn it on, all of a sudden you're sort of almost overwhelmed by the data. So this is north of Detroit, one of the watersheds we worked in, where storm is rolling through, and all of a sudden, all these invisible components of the infrastructure in the watershed become visible, and they become overwhelming with the data you collect, right? Like problem number one, when you solve the data scarcity problem, you create problem number two, which is what do I do with all this data? And so we've been working on machine learning models that take the amount of data that we have and learn sort of forecast models, right? Like given rainfall and runoff behavior before, as we just talked about, a classic regression model of fitting a line is not going to do it. We need something else. We also, we learned throughout this, without going into the details, that neural networks need a lot of data, so you can't use those. And so we got to find some parsimony. We got to find models that actually work for this. But we've been deploying these, and these are actually running live right now. It's taking the data and it's forecasting into the future and sort of telling us what's going on and enabling simple use cases. Like if it's flooding at this bridge or it's about to flood at this bridge, maybe we can sort of alert people, send out text message, etc. So this is just, again, in the context of recent news, these are the kind of applications you can explore just by having data and predictive models. So that's one thing, but I'm going to go back to the self-driving car analogy. What if you don't like what the water is doing? What if you want to change the flows or change the behavior? This is what we started doing, like almost like, I want to say easily over 5 years ago, about 8 years ago. This is Brandon in the background with one of our valves that we purchased. The county, Washtenaw County here, we worked with them to retrofit infrastructure that was built in the 70s with internet connected valves. So like rather than building new infrastructure, we go into basins where before the water would go in, the water would go out. You now have this internet connected valve. You're measuring the water levels. You close the valve to hold back that water. You let the sediments trickle out, and then you check the weather forecast. And if it's about to rain, you create more storage. So it's this dynamic system. And what we've seen just at the site scale is that you get a tremendous amount of benefits, right? Because no longer is it doing what it always does, goes in, goes out. By strategically controlling retention time and all these different things, we've seen just basic things of increases in sediment capture, as would be expected, both in dissolved and suspended cases. And where things get really interesting is when you start stacking these across the watershed. So going back to that example earlier, optimizing at the individual site level can only take you so far. What if you want to have watershed scale impacts? And we can, look at a conceptual example of maybe two neighborhoods where I have a downstream point. When it rains, it floods. It's because neighborhood number one and neighborhood number two just drain downstream. And, that's what's going to happen every time it rains. But what if we know, for example, it's raining a little bit in one neighborhood, but a lot in another part of the neighborhood? Maybe we can close the valve in one of these components, let the other neighborhood drain out, and then dynamically, based on the storm conditions, taper that hydrograph downstream, really start controlling downstream based on these conditions. And again, evoking this idea of a self-driving water system, depending on the storm event, really starting to scratch at this idea of an entire watershed that's being operated differently, autonomously in different conditions. And so we've been exploring this for quite some time here. This is one of the test cases. This is actually that watershed I was showing you earlier with that silly Bob Ross example, covered in sensors. We've had valves there. We're now testing in different locations. But I just wanted to show you a case study that really sort of like helped take this from conceptual to real. So this is the basin that I was talking about. Built in the 1970s. We sort of co-selected that with the Water Resource Commissioner here, and he was open to it. And we're very, very fortunate to be able to work with them. Usually when it rains, the water flows downhill. It actually flows through this treatment wetland that the city invested lots of money into. I forget the exact price, but we're talking about millions of dollars easily for infrastructure construction. And when it rains, the water is supposed to flow through this naturally constructed wetland before it goes to the river. But as you can imagine, no infrastructure asset is large enough. So when it rains, you get overflows, you get flooding. And so the idea was pretty simple here in that system scale example. Put a sensor downstream. If there's treatment capacity, if there's room downstream, open up the valve. If not, hold back that water upstream. And that's kind of what we did. So after a rainfall, we're holding this water right here. And this is, again, just videos that we took of this along with some data that we collected. It just rained. That water is being held upstream right now, right? So now we're using that asset in a way that wasn't used before. When we know there's room downstream in the wetland, we open up the valve so you can see the water levels in the basin are decreasing. And about an hour and a half later, we're starting to see the water levels rise in that downstream location. And the water levels in this video are changing from that red location to the green location as in these marks show over here. And because it's not raining, we know that the only thing affecting these water levels are students in the lab controlling the system. it's quite powerful when you consider the fact that this is miles apart at the scale of a watershed. And what we learned by working with the county on this was that effectively by doing this, by not overwhelming this downstream location with all of this water all at once, it acted as if it was twice as big, this equivalent, right? So in order to handle all that water that would need to go down there, you need to build the site twice as big. You can't do that because there's parks, there's homes, we're boxed in by development. And so this notion of a digital upgrade, by controlling a valve in real time, you can squeeze more performance out of the system. And that's in the words of the resource commissioner who taught us that terminology. I have infrastructure, and before I build more, I can maybe consider how I can get more performance out of my system. And I think anybody who sort of just even pauses to think about it remotely, there's always room somewhere. You just got to find it and you got to detect it in real time. And that room might be here one storm, somewhere else another storm. And so building these dynamic systems allows you to just squeeze that performance out of it. And the city and the county did their own calculations, which just in this case showed that by simple addition through just one valve across this kind of like small area, it's the equivalent of saving millions of dollars. And so what that led us to was saying like, okay, well, now that we know what's possible with these stuff, what can we do? Like flooding is obviously one way to look at it, but could you start controlling water quality across the whole entire watershed? And so we started building these tools for modeling that basically said, okay, well, we had detention basins, retention basins. These are similar to treatment components in a treatment plant. And so we started building these models that basically allowed us to start treating, at least computationally, the watershed as a treatment plant, and now imagining that operators can control the whole entire watershed and seeing some really kind of fascinating results when it comes to water quality. And so before, it wasn't feasible to think about it that way because you're not really controlling anything. But now that you're controlling it, we have the knowledge in the field, broadly speaking, to start thinking about it that way. And so what we've been pondering for quite some time is just how do you take the knowledge that we have as water resource engineers, as environmental engineers, and embed that in a new generation of algorithms that traditionally come from other fields, computer science, electrical engineering, et cetera. And there is a ton of stuff to go into. And for the sake of a lunch discussion, rather than getting technical, I'll just show you that there's a ton of different approaches. Some are rule-based, which is typically what we do in treatment plants. If this happens, then do this, right? Some are maybe more dynamically based. So this is more mathematically oriented, but these are the kind of algorithms that maybe run on airplane autopilots. And some are really kind of on the fringes of maybe even using neural networks and kind of autonomous agents to start learning how to control these systems and getting them to sort of achieve what you're looking for. The point is, it's all of it is just a bunch of math. And this is the part where I usually show a lot of math and all the stuff that we do, but I'll skip that in this talk because it's more of an overview just to show you that, once you start implement this math, which again starts in the 50s and evolves through the following decades, it has a profound implication, at least on the control of our stormwater infrastructure. And so when we think about stormwater systems, usually they're going to be hit by a certain size storm and a certain length storm, right? When we think about storm intensity and storm duration, every system is going to have a breaking point. Infrastructure is not designed to contend with everything. But what we discovered through the research is that when you apply real-time control without building anything new, just by dynamically controlling these things, you push the performance boundary. You basically take the original breaking point and you sort of push it outwards through digital upgrades, which is a strange way to think about it. And we did a lot of validations, a lot of mathematical models, a lot of simulations to basically show how these performance regimes expand as you add real-time control. So, one thing was possible before now, more things are possible with once you add real-time control. And so a lot of that is quantified. If I had to sum it up, basically, again, if you just had a rule of thumb, if you add real-time control, your infrastructure acts as if it's twice as big. In most case studies we have, so that's not like vetted across everywhere. Or if you want to put it differently, if you're building new infrastructure, you can make it half the size with the same performance, which all of a sudden starts talking about, okay, what else do I do with that land? What does that mean for development? This is being explored globally. If we look at cities across the world, depending on where we are, I'd actually say the uptick is maybe higher in Asia and Europe, but the United States is working its way toward there. And we can look at lots of cities, going back to South Bend, Indiana, when they were looking at it with embed and those folks who worked on it under Mayor Pete, all the way down to some new cities that are exploring this. I'll give you the example from Detroit. It's not just for separated stormwater systems. You can look at it for combined sewer systems. And if we look at Detroit, At the Great Lakes Water Authority, which is our regional water authority, one of the largest in the country and in the world, with the largest treatment plant, depending on how you look at it, they can control assets underneath the ground, like these inflatable pillows that are, situated in a 20, 30-foot sewer pipe. And by pressing the button, you're effectively converting that linear asset, that pipe, into something like a little dam underneath the ground. And the students in the lab did a bunch of analysis a few years ago that showed that these digital upgrades, but just by changing how you're operating your pumps, like think about reprogramming your water infrastructure and helping the operators do things differently depending on the storm event, just in portions of the system could be the equivalent of billions of dollars of infrastructure investment. So again, like if we think about, when they tell you like call before you dig, when it comes to digital solutions, it's worth looking at what are your digital assets, what are your physical assets, and can we sort of operate them differently before we invest into new stuff? You're always going to have to invest into new infrastructure, but by adding these upgrades, there's other considerations. So I'll pause for a second there, but basically that's I see you turn around your camera before I give the other example. Yeah, go for it.
So, a quick question that came in from the audience, right? So it kind of gets to this GIGO that we were talking about in the green room, the garbage in, garbage out. Let me read the exact question and get your response to it. But the point about unintended consequences also begs for comprehensive system model refinement before infrastructure development. Can you start with known data, or should data needs be defined first?
Wow, that's like one of those questions we could spend for an hour. It's about looking at ours. So a couple of things, unintended consequences. Let's start there real quick and talk about when you roll out new methods, and this is true not just for this digital technology, but other stuff. You're always beholden to show that like what are the risks. Oddly enough, we're not talking about the risks of business as usual. We're building new stuff and we don't know what's going on because we're not even measuring it to begin with. So yes, we have our models, but ultimately what's going to happen, and are we moving the needle forward? Like, did the Clean Water Act work? I don't know. Do we know, right? And so it's really, really tricky. But the same tools that we use to plan for new infrastructure, like take the stormwater management model for a lot of cities when it's sewers and separated systems, we can use those tools to explore real-time controls, do the equivalence analysis, bring people up to speed. And then this question of if somebody wants to work their way up to real-time control, like a utility or municipality, you don't just turn the keys to the self-driving water system on day one. What you do is you make a plan for where are blind spots, where are pipes clogging, what's going on. Okay, now can we get the operators on board? And we'll talk about this in a little bit, to sort of like explore these technologies. Then in most cases, you're never going to go 100% autonomous, let alone, I mean, at least for now. Operators are in charge. So how do you build decision support systems for them to have a proactive way to sort of manage these systems? And then if you reach that part, then maybe you turn the key to the self-driving. I think the point of today is to show what's possible. It's not quite what's real yet, but there are cities exploring, like we think about Buffalo, New York, they're exploring autonomous control solutions, if not at least some of these decision support tools. So again, it is a stepwise process. It is by no means turn it all on at once. We can't take too many risks, obviously, with the stuff, but there's kind of a hierarchy of how we can, take steps and get there responsibly, hopefully.
Thank you.
Sure. So that's for stormwater systems. We can kind of, without going into repeating the whole story, we can think about drinking water distribution systems. I remember we had a student here, and this is a collaboration with Krista Wigginton and Lute Raskin. We talked about, what could this mean for drinking water systems? So just like stormwater systems, we don't measure nearly as much as we could. Should we, is a discussion for later. But we talked about, we measure oftentimes at the treatment plant, maybe sometimes in the distribution systems, but do we really know what's hitting, what the water quality is when it hits the tap? And that's where we developed, the lab developed these internet-connected drinking water quality sensors that we could put underneath people's taps. And we evaluated this both in Ann Arbor and originally actually starting in Mexico City to try to figure out what is the water quality arriving at the home. Because oftentimes as engineers, we do this stuff and then we say, well, I did what I needed to do, let it go to the residents. And sometimes you grab a sample from their tap, but really what's happening at the tap? And so we started seeing lots and lots of dynamics. Needless to say, just like with stormwater systems, when you measure in places you don't usually measure, doesn't match the model, it behaves weirdly, and we measured a lot of different parameters. One of the ones that we walked away with that was maybe most interesting was the relationship between the residual disinfectant concentration, meaning how much chlorine do I have in my water, or chloramine, depending on what you're using to do disinfection, And how does that relate to one of these sensors that's easy to deploy? And in this case, ORP, right? Oxidation redox potential. And as we know from just textbooks, like there is a relationship between these things. And depending on the disinfectant used and all these other parameters, we start seeing this relationship, which basically says, if you develop a machine learning model that can tell you, given this ORP concentration, what do I think the residual disinfectant is? Couldn't I train some AI agent or some algorithm to basically say, hey, ORP is changing. That means water age is changing, disinfectant concentration is changing. Go ahead and flush that tap autonomously, flush it out and see what happens. And we actually built this system. So Ernesto put this together. Along with the sensors that are measuring water quality, we are actually also controlling the valve. So before we used to tell people, hey, go flush your faucet and put your finger underneath the tap, and then when the temperature changes, you're probably okay. In this case, you have a system that's automatically doing that for you in the morning, at night, depending on how the conditions are changing. And we saw some really cool impacts here. So this is just a study, and I think this was in Ann Arbor or Ypsilanti, in any case nearby here, where as you flush the system, the temperature changes as you would expect when you put your finger underneath it, but also the algorithms could use both temperature and ORP to do the real-time control. And so again, just showing you that it doesn't just apply to stormwater. You can think about these things both in terms of drinking water, or in this case, resource recovery. So I've been part of a project with lots and lots of folks, hard to mention them all, funded by the Department of Energy with WRF, who's a prime on this one, looking at what are the implications of AI, and this is an AI-generated image, obviously, of energy recovery and resource recovery at treatment plants. And so before I show you that example, I just wanted to show you, and this is just a segue for what oftentimes for those of us who review scientific papers, the kind of stuff we see in the era of hype. A very common thing now that we see is people get excited about how much data we have. Hey, I'm operating this facility and I got terabyte of data, gigabytes, many terabytes, whatever. And they show a time series of it, a really complicated thing. Maybe it's like the effluent concentration over time of some parameter they're interested in. It looks like a complicated data set. There's no way you can fit a line to it, right? Like it's complicated. But if we look at these data, we can oftentimes see through basic kind of analyses that really complex looking data sets are actually a summation of very simple things. In this case, two sinusoids, a sinusoid, another sinusoid, they add up. Each one of them looks simple, but together they look complicated. And as we know from, again, middle school or high school math, depending on when you took it, a sinusoid is fully described by its frequency and amplitude. And so if that's the case, instead of having terabytes of data, I only really have 2 data points in here. And so what I'm trying to evoke with this is, before we get really excited about how much data we have to think about how much information is in that data. And those things are fundamentally distinct ideas. Really complicated data, even if you have terabytes of this kind of stuff, could just have one single data point in it. And so even though I think we're going through this period patting ourselves on the back about how much data we have, we think we're data rich, but we may be risking being information poor. And so I'm putting this image on here to just evoke this notion of our data cup in the water community. And this is an opinion now, because how do you prove it without going case study by case study? But I believe that our data water cup is not nearly as full as we believe, because there's less information in these signals than we realize, which leads to sort of interesting things that you come up with. And I'll show you this example of DC water that we did with as part of this DOE study. So here's Heidi. Heidi's one of the engineers, one of the researchers at that plant. And I'll focus on an example of making some cake. This is the terminology that they taught us. So we have these dewatering presses. And so the effluent, or part of the effluent that goes through here, basically what you're doing is you're sort of squeezing the solids out on these presses. The solids come in and the mix comes in. It's got water in it. You're trying to remove the water by adding polymer. That costs money. It's associated with energy use with the press and all these different things. And you're building this cake. And ideally, you'd like to add the right amount of polymer in order to be able to do that. And so we could add the right amount of polymer to do this dewatering if we just knew what the solids concentration is. But to know what the solids concentration is, you got to go in and grab a sample every time. And that's just not feasible in real time, right? And so the idea was, could we estimate the concentration of the stuff going into the press by adding these like acoustic sensors, effectively listening to the pipe, if you will, listening to the pipe and being like, hey, based on the sound properties, the acoustic properties of the signal, or maybe the accelerometer readings in the pipe, we can estimate total solids by calibrating it with these lab samples. And so classic machine learning problem. You got total solid samples from the lab. You got this streaming acoustic data. You got a machine that learns the parameter to some simple or fancy model, depending what you have. And then that tells the operator, hey, this is your TS concentration. And we had a lot of data. We started off with like many gigabytes of data. Again, when I review papers, I got so much data, right? But if you do something really simple and very boring to a lot of people, especially students who want to like run deep neural nets from day one or second one, if you just take the histogram of your TS concentrations, you'll find out that it doesn't vary that much. Well, why? Because the operators are doing a real good job training, running this plant. And the TS concentration is going to be steady because they're following procedures, they're following permits and all these different things. And so this thing that seems like a ton of data actually is not a lot of information because they're mostly doing the same thing. And so again, it evokes this idea of be very careful in the era of AI and machine learning, because you may think you might have a lot more than you actually do. And sometimes these boring seeming tools like just plotting it over time or taking a histogram, or taking the average, may show you very quickly that you need a lot more information. And if you want to create reliable models that don't just work for the average, you want them to work across a band of inputs, as we just heard from earlier from the prior questions. Boring data is not going to cut it. You got to go to your operator and say, hey, I need you to run this plant through the paces, low flow, high flow, all these different things, because I'm just trying to collect some really interesting data to train my model, see how they respond to it. But that's effectively what we had to do with DC water, is basically say, we really do need you to run it through its paces to understand what the low flow, high flow scenarios look like, low concentrations, high concentrations. Because when I plot that histogram, no longer am I between 8 and 12, I'm actually between 1 and 20. And that's very, very different, because when you're building models, oftentimes what we actually want to predict is not the day-to-day scenario. We want to predict the interesting times when it rains or when it's really, really dry, but we don't actually have that training data. And so when you're building machine learning models, I guess the word of caution, inventory your data, try to understand it. You don't need to be a computer scientist to do that. That's literally where you rely on your sort of like domain expertise. And only then will you know, can I actually train my model? Because for most, like a lot of the papers that I review, people get annoyed at me so much. But I'm like, hey, I took the average of your data and it does a pretty good job predicting the same thing you're predicting with this incredibly complex neural network model. And why is that? Well, the effluent concentration is regulated by operators who are actually doing a pretty good job, a really good job operating these plants. So it shouldn't be surprising that my guess of the effluent concentration is usually the same is a pretty good guess. And so if we're building models, we need to be asking ourselves some pretty good questions about, do we have enough data, let alone should I be building this to begin with? And most people don't do that. They just throw neural nets at the problem and off we go. And so that's kind of the where we are component. So we covered terminology, we covered where we currently stand with what's feasible across like 3 examples of stormwater, drinking water, and resource recovery and energy. I just want to close really briefly with what I think we're beginning to sort of see, at least in the technological realm, and what that means for water, the water community in general. But I'll pause for 10 seconds just to take a breath, because I know I'm kind of covering lots of different things.
I'm happy to come in.
Go for it.
Yeah, you're stimulating some questions for folks, and so particularly when you were looking at data, one of the folks one of the questions that was coming in here, and I'll just read the specific question. Is the question of data set size just basic statistics? For example, are we adding too many factors? Are we adjusting for collinearity?
So the question of, and again, not to rephrase every question, but there's sort of like flavors of questions that come up, and one is oftentimes, what's enough data? Like, people know that machine learning models can do a lot of stuff, and then the question is like, how much data do I need? Well, that's oftentimes guided by, again, going back to domain expertise. Plotting your time series, oftentimes that's the most confusing one because there's a lot to see in there. Plotting histograms, plotting the frequency transforms. These are all things that we already know how to do through other applications. Will give you some insight into what you have, but a basic min, max, and mean and standard deviation will give you a pretty good handle of the range that you're in. So just like you were saying earlier, sometimes fitting a line is not the best model because it's not representative of the data. However, you know where that line's going to go. So when you're extrapolating outside of your data range, at least you know where it's going to go. With something like a Gaussian process model, a neural network model, XGBoost, when you're outside of the training range, who knows what's going to happen. And that's why self-driving cars sometimes flip over, because all of a sudden they see something they never saw, like a little gnome on the side that they never had a photo of or whatever, right? Um, the more profound question that people are also asking in this chat is kind of notions of collinearity. And like oftentimes we put correlated data into a model, like ORP and water temperature in the case of the drinking water example are actually oftentimes going to correlate. Is it important to tease that out and only use one of those? The technical answer is yeah, and that deals with model stability and a lot of other sensitivity kind of things that we can get into. That's good, but that's also the sign of somebody who's kind of, whoever's asking that question, I'm not seeing the name, is thinking through this in a wise way. They're getting to that next step. So all these things are important, but what's oftentimes important is that basic boring step. And that's hard part, especially, again, I'm super excited with what students want to do these days. They're excited about these tools. And especially now with AI coding buddies, jumping into a deep neural net as your core model or jumping into XGBoost on day one, we need a baseline. And oftentimes the baseline is very boring. Take the average of your data and see what you get, and if that even makes sense.
Perfect. Thank you.
We don't have baselines. We just know things work well. Okay, so again, maybe I'm just saying this because I review a lot of papers, and it's like, oh, if you just did that, we could just get to the content rather than talking about how many parameters your model has. But anyway, I'll close on what we're looking at right now. And that's maybe, this is touching upon maybe some uncomfortable things. And I want to close on a photo that I really like. Maybe I'm just jealous that I don't have one like this. But this is Norbert Wiener. He was one of those mathematicians from the 50s, even before, posing in a classroom with math in the background, a robot, and a cigar, a ridiculous photo. But anyway, he was one of these math people. And he wrote this book called On the Human Use of Human Beings. I do not recommend reading it. It's actually not that readable. It's still a lot of math. But kind of talked a little bit, at least based on my interpretation, upon this thing of like, these intelligent systems are coming, automation is coming, and it's going to disrupt people. And so what we need to do is focus on making the math really, really good, right? Like if we just make the math really good and we cover all of our bases and all of this is there, the modern equivalent is solving the alignment problem of AI. We're going to test our neural networks and make sure they do all these things that are responsible. If we could just focus on the technical challenges, we will solve the societal challenge. Even though I think that's important and I like it, I think the part that gets missed a lot is the human side of things. And I'll give you the example that really kind of like set our lab into a completely different direction about a few years ago, where we looked at technology adoption in different fields. And one of those fields was air traffic control. So air traffic control, just like controlling sewers or other kind of things, complex problem, lots of different things flying around. And the natural solution would be like, hey, instead of doing it manually, why don't you bring computers in and dashboards and all this like VR and all this other stuff? And what they found out is that if you just slap technology in front of these air traffic control operators, they could tend to ignore it. They started passing paper strips between themselves, circumnavigating the technology. And I think that's at the core of it, is if you just focus on technology and making it as good as you think as a scientist or engineer it should be, you're missing the mark in terms of trust and adoption. And that has to start from day one. And that's depending on the fields you look at, like in computer science, that's the field of human-computer interaction, user experience design, UI design, things like that, that we're not trained in as civil and environmental engineers or scientists. However, it's important. And so that's where I kind of wanted to close on this idea of the digital water stack. When we think about the adoption of AI systems or digital water systems, whatever you want to talk about it, there's a stack that starts very early on. It starts with the hardware and the sensors, the analytics, the user interfaces, and we'll close on the agents in a second. I just wanted to tell the story of Brandon. I think, he was wise to understand that if you're going to increase the number of measurements across the United States when it comes to, let's say, natural water systems like watersheds, you can't just expect everybody to deploy sensors. It's at some point it does require a technician or like an electrical engineer, and so we have to move from these big boxes, engaging stations that work well but are not scalable, to easy to use systems. There's a clear distinction between usable and useful. Stream gauges are useful, but they're not that usable. And so what you put together, and this is part of Hi-Fi, the group that I work with outside of the university, is ease of use at the beginning. So here you see a water level sensor. It's connected to the internet, just like the other ones we talked about, but it's kind of like the old school Netflix model of DVD in, DVD out. Anybody that can use a screwdriver can go in and replace the unit, and then a new box is already in the mail with the new unit. You pop it in, send the old one back, shipping included, that kind of model, to make it very easy for somebody to collect data, because that's been stubbornly inaccessible and required a lot of expertise. And we've been testing that. Brandon's been testing it with water resource managers and operators across the United States. And again, showed that if you make it really easy to collect data, you have to solve problem number two, of making that data useful, like turning it into some actions. And that's where these analytics and AI come in. So enabling things like alerts, detecting events, managing your systems day to day. And that's sort of manifested in an end-to-end solution. So like as soon as a sensor goes in, which is easy to deploy, as I would say, it's hard to find easier to deploy sensors because it is a hard thing to do. All of a sudden, all that stuff gets analyzed in real time and produces maps and insights that can sort of help you close off roads, plot these flood maps in real time, really turn that data from something that all of us, I think, would agree is useful into something that's usable. So you have to tackle the stack all the way across. And that stuff is deployed in lots of communities across the United States. I'm showing an example of New Orleans over here where it survived various hurricanes and other things and is being used in real time. So these technologies that we thought about in lab for a long time, turning them from something that's bench scale, lab scale into something that's really useful by people who have to make day-to-day decisions about water systems. It starts at the physical level of the actual hardware. And we've been exploring, what that means for various applications. And I'll show you the stormwater example over here, where we deployed lots of these green infrastructure sensors. They just basically measure water levels in rain gardens and green infrastructure, and all of a sudden hit you with this wave of data of how these assets are performing. Hint, it doesn't perform like the model. It just gives you all these different kind of data sets. And rather than looking at all this raw data, which shows unsurprisingly that every site is different and every location is different. And why is that? Well, instead of just looking at it, which oftentimes, again, I said is step number one, you should do that. We can now train learning models to sort of say, okay, could we predict where green infrastructure would perform well? Where is it going to pond? Where is it going to flood? Where is it going to drain really well? And we can kind of create these data-driven maps, like solely informed by data that can give us a snapshot, for example, of Detroit, of where GI would perform well. And so in these blue areas, we would expect fast infiltration. In these other areas, we would expect low infiltration. And that is taking raw sensor data, easy to deploy sensors, doing these analytics on it, and finding out that design factors and location and soil types, at least in Detroit, were not the major factor. We found out, for example, there that groundwater was the leading factor in terms of how the stuff performs. And so if we just rely on put it everywhere and it's going to work just fine because the soil types, it just wasn't the case here. And that's why it's important to measure. And so we've been thinking through, okay, well, if that's useful to us as researchers, could we put that onto a map for residents to look at, maybe the managers to look at in the city? And so that's where we came up with this little video game called Sewer Tycoon. Okay, here's your infiltration map. So when you're citing GI, maybe you can use that as a guide. And then the idea came up, well, what if you could edit it? Couldn't we make it possible for a user to sort of then say, what if I added some rain barrels, green roofs, etc., almost like a little video game to make it really easy for non-engineers to deploy this. And that's effectively what's running right now. So if you want access to this, you should ping me. We can give you a username and password for this. Imagine being able to run a really complex stormwater management model, the same that's run by sophisticated engineers and utilities, but made so easy to use at the interface level so that residents and planners and others could do it at the level of a video game. And that's truly what's possible now. So again, when we're looking at the smart water stack, when we talk about adoption, we have to be really cognizant of the fact that it starts at the hardware layer. The analytics we can handle, but then the user interfaces matter. And now we're getting to that final step that's, one could argue, just a few months old. And this is, we're going to talk about agents for a second. So imagine a non-expert user. We talk about impacts to workforce, maybe a water operator who traditionally would have to go to a consultant and ask questions like, can you run this for me? They run the analysis, they produce a really long report, you got to read it, all these different things. Wanted to ask a question of their system. And this is a demo that's 1 day old. So I'm going to show you a video of something from yesterday. So this is like unpublished. I'm just showing you what's possible right now because the stuff is moving at a breakneck pace. This is a classic LLM. This is Claude. You can do this in other LLMs. It doesn't matter what it is. And I'm asking it, hey, what's the flow in my link for my largest subcatchment? Just a regular query in regular English that could be asked by anybody. You don't have to be a professional. And the model says, hey, I ran all these things for you. I understand what you're asking based on your thing. The largest subcatchment is this big. This is your flow coming out of it for that particular event. What do you think? Would you want me to plot it for you? And it's like, yeah, plot it for me. And here's a summary of the report that it ran. One question that could be asked by anybody without needing to know fluid dynamics into a large language model that then spits out a full-blown report in terms of what's happening. And that's kind of where this notion of agents come in. An LLM on its own does not know about your system. It does not know about your reports, your permits, let alone the tools and the models that you're running. But this demo right here, as of yesterday, we had like a meeting in lab. We started connecting tools. In this case, the stormwater management model to the LLM. And frankly, for me at least, it was kind of a point of like, oh, geez, this is what's possible. Because now we're connecting through language to these models that were required sophisticated modeling and all these other things to allow users to just ask these kind of questions. And what that beckons is this idea that like, well, these agents can do these tasks for you. There's lots of tools out there, lots of different things you can connect them to. What does that even mean about the users? Could they autonomously do these kind of things? And the answer is, I have no clue. This is literally like we're flying as we're learning, as we're doing these things. And it creates lots of questions related to, and I think a lot of us are curious about this right now. What does this mean about the workforce? What does this mean for people who are experts now, but these models can replicate that expertise? What does that mean about trust and automation and risk taking in the water sector? And I think those are the kind of interesting questions that we could be discussing. I'll just put those up to sort of just like propose some of those. Obviously happy to go through anything. And this is the crew that built all this. It's been really exciting to work with all of them. So I showed you again the terms, what's possible now, and as of yesterday, what's possible as of yesterday. And I think we can now chat about, should we be doing this, and what does this mean for whatever. So
Brego, thank you so much. This is fantastic. We really appreciate you being here with us. I'm going to ask if you would, if we'll pull down the slide, and then that way people can see our ugly mugs back side by side. Well, maybe my ugly, yours less ugly, but so we're gonna go back, and we've got some questions, and they kind of fall into the bins of kind of how you gave your presentation. So we've got some that are going to go back to the background. They're going to talk about some of, current status of the tools for looking at the accuracy of them, ask specific questions about Power BI, and is that part of AI? Then we're going to get to some questions in the case studies, and that's actually where I had already written down some of these things you brought up: the responsibility, security, workforce, the interprofessional space. So we've got some, and I think maybe talking about those in some of your case study space can be helpful.
sure.
We've got some folks that are asking some questions, particularly about the data in the models. So, is what we need outliers? Can you talk a little bit about models for detecting anomalies versus models for optimization? Can we talk a little bit about our understanding of mechanistic models and cause and effect as compared to statistical models, and just, hey, they correlate with each other? So we'll talk about that a little bit, and then ultimately we'll end a little bit more in this space that's kind of looking over the horizon. People have got some questions about, like, how does climate variability integrate into this? You were talking about useful and usability, so there's all of this kind of stuff that we learned from COVID and citizen science all the way to today. And so there's these questions about, is there almost a replacement from some of the public good of government by the citizen science and access to this? And then kind of the next on from that, is that actually going to lead to a less equitable world? Because, part of the benefit of government is that it aggregates together and we're all sharing in that. But if I can just go off with my own resources, my own intelligence, my own pocketbook, and do great things for myself, boy, is that going to lead to things perhaps less equitable or not? So those are speculation. And then ultimately we'll conclude with our kind of standard question. What would be your advice for the seasoned professionals, for the emerging professionals, for the students? So we'll kind of pick those up in bins. So if we can go back up to the background part, we got a couple of questions from the audience. I'm going to kind of read them verbatim and let you hit those. But the first one, what's the current status of tools for checking the accuracy of LLM products? For example, it's clear that LLM can be used to produce a review paper on a specific topic of interest. From my limited experience, the results would be pretty good, but is there a way to assess the accuracy at present beyond like manual reviews by human or groups of humans?
Yeah. Okay. So that's a really good question. So presently, the performance of these models is like a massive talking point in the tech sphere, if you will, right? So you can go to websites and see which model performed the best based on various benchmarks they give it. And those benchmarks are broad. And a lot of those benchmarks also focus on safety and security. And depending on which benchmark you look at, some are good at image generation, some are good at like writing, some are good at code, right? So you can look at there's some very strong opinions without promoting one over the other over which one is really good for programming versus which one is good for writing, which one is good for all around. Um, and companies pride themselves on these markings and they tune these things to accomplish that. Um, that is being done, I would argue, in a way that like is pretty sophisticated. People are doing it. It's not something I do. I like stay on top of it just to see like what's good and what's going on. Um, I would say when you focus specifically in on some field, that's where things get interesting. I don't think we're tracking what the best LLM is for environmental engineering because none of them are tuned to that. When you get to the specific application case, it's a little bit of a wild card, but that because you don't know, you have to check it. And I would say like checking for accuracy should be part of every workflow, even if it's fully automated. So like, like if we're worried that these things are producing wrong answers, well, then we should be looking at these answers and making sure they're correct. We're trained at this, right? So hopefully, like getting complacent is a risk to all of these things, and we should be double checking it. But I haven't seen like a ranking on all these different things. I would say though that like probably you increase the accuracy. Like in the case of a review paper, assuming you have the permission to retrain the model and provide context with all this copyrighted material, if you
Right.
put it in there, I wouldn't be surprised that a publishing company or an organization like this that publishes stuff could create a finer grained model with the context length that it has that answers these questions better than others. So I know this is like a long-winded answer to that question, but like double check the answers always, even if it's generated. And I think that's where the benefit is of, when I say our generation, we learned it old school. Like we had to learn all the things, and now we know
Right.
where the mistakes are, which actually amplifies our ability to work on these things. There is a little bit of a risk that if you're not paying attention in the classroom, you're just using an automation, you might get a wrong answer and not know what it is.
Yeah.
So ultimately, are agents going to cross-check each other? Maybe. It's always good, just like in anything else, like in business, it's good to have competition. So maybe looking at different models and comparing those answers is the way to go. Maybe it'll be
Perfect.
automated one day. We'll see.
No, I like that. I like that. So now this another specific question, this background is Power BI, business intelligence, part of AI with a lot of data that we are dealing with in the wastewater industry. Do you think we can use Power BI to visualize results and make decisions? So I know it's a specific one, but maybe if you've got a view on that.
Yeah. I presume maybe that question comes from the fact that the use of Power BI in this case is an opportunity for somebody and they're weighing, should I use this over something else? You know, I always encourage people to say, like, it's not always one choice in front of you. You should at least have two or three choices and say which one works better for me. So, is Power BI, does it work for you? Well, it depends what's your other alternative, right? Like do you even need it to begin with and all these different things? Um, is it AI specifically? Well, I presume based on what I know about Power BI, it has a lot of visualizations and trends and all these other things. And they, like other companies, are probably taking advantage, I would guess, of sophisticated code in the background that runs these trends and stuff like that. So I can't promote one tool over another. I'm actually stubbornly manual. Like I write all my code still to this day. That's actually where these coding tools are really good. That's what I would recommend for students. So without knowing the specific use case, what I would at least recommend there is if you're considering one tool, especially commercial tool, consider like two or three more, maybe consider an open source solution, test it because no door is closed. Like if you say I'm using this tool and I close the door and I'm gonna use it for the next 10 years, get away from that mindset and say, I try it, it works well, but the user interface is bad, which is actually true about a lot of municipal software, then get away from that one and try a different one. And so get some more options and then pick from that, or we can talk about the specific use case. Happy to talk to that person.
Perfect. Fantastic. So now a couple of kind of like rapid fire in this kind of like idea of your case study, right? Whether you're talking about the car or the automated run itself, citywide, urban
Yeah, yeah.
waterscape, right? I mean, ultimately, like the physician is do no harm, right? So let's think about the responsibility for this. Let's think about the security for this. There's these valves all over the place. The bad guys can get into this. Let's think
Yep.
about the workforce. As humans become more reliant on this, do we pick up a certain bunch of lazy habits where we miss stuff? And let's talk about that interprofessional space, right? Like the urban planners would say, Bronco, it's not up to you to do these valves. That's why we have zoning
Sure.
rules. So,
That's fair.
yeah. So can you
Yeah.
speak to some of those issues there?
Yeah. Well, I could see implicitly how it seemed like that I'm like promoting these things, but really what it is we study them and we say, hey, that's pretty, like, look at these differences, right? Then let's have the honest conversation about what it brings to bear. So again, like, just like the Power BI question, it's not should we do autonomy? It's how does it compare to existing approaches? Is it complementary? Should we do one over the other? But it has to, the conversation in vacuum is always really tricky. And what I tell people is any approach has risks. Building classic infrastructure, which we still need, not to call it classic, but the stuff that we know how to build, has its risks. We should hold that to the same level of standards. Say, can that cause flooding? Can pipes clog? Yes, pipes can clog. So, all that being said, when you consider a new approach, there's always going to be pros and cons. There's no silver bullet that's all positive. And you have to be able to, in the classic engineering sense, be able to weigh the benefits and the risks and make your own decision based on what works for your own system to be able to make this determination. That is guided by factors that are outside of my academic knowledge of what guides like people's stuff, like their importance and all these other things. But yes, it's true that if you connect infrastructure to the internet, with the pros come the negatives of like, oh geez, what if this is hacked or whatever? No, it's not inconceivable that anything can happen. But again, you take precautions in a lot of these systems. As I said, you don't just turn it on from day one. You measure, you get everybody on board, you kind of add it to the system. You put safeguards in place. If connectivity goes out, the valves can open, just be in an open position, which means it's just in regular position as it always was when it was constructed. So technically, the autonomous systems, you can build them in a way that they should not perform worse than static infrastructure, right? And so if you take these considerations in place, have overflows, all these different things, then you can look at it and say, am I doing the best possible thing? Meaning in our case, like our encryption algorithms are the same that banks use. So like I can't think of a better one at the moment, at least. If you take all those steps, then do you and your organization believe that this provides sufficient benefits to deal with whatever adverse impacts can come? And municipalities and utilities have solved this different ways, right? You go to some treatment plants or resource recovery facilities that are not connected to the internet, yet they have a local network. Some use, internet connected devices. It really depends on the comfort level and the organization, but it is true. You need to consider all these things. There are risks to this as there are with everything. And if we can just compare all these things on an equivalence chart, then somebody based on their knowledge of the water system should be able to make that determination and decision. It's not just one over the other.
So that's where there's still going to be plenty of room for the lived experience of the knowledgeable experts to come in and beat each other over the head with their expertise and preferences
Right.
And wrestle it out.
Discourse is good. Exactly.
Fair enough. Fair enough. Okay, so now pivoting a little bit to the ones where you were starting to get into some of the drinking water and thinking about, some of the data. So a question that came in here, it felt like maybe a little bit you were talking about that it's important to kind of know some of the outliers in our data. Is that too far a statement to say, hey, we need the outliers? Because you were talking about well, gee, take it through its paces, right? But but if you extrapolate on a linear regression, you know where you're going. If you extrapolate in a neural network, who knows where you end up? So, is there something to be said for when we're trying to deal, and this is going to lead into, things like the climate resilience or these black swan type things, right? So,
Yeah.
yeah. So what's the role for outliers? What's the role for lots of core data? Can you give us a balance there?
Yeah. I mean, like outliers are going to be part of any data set, right? And that's what makes maybe machine learning models more sensitive to it. And it depends on the model, right? Not all of them are, because some are really impressive and they're able to handle that. We can get into that. But we have control. Like when you're building a mechanistic model or you're building that regression model, you kind of know where your outliers are sitting, and that creates a level of comfort. So there are methods, like what I tell students oftentimes, or folks that we work with, is the boring part about building a machine learning model is that sometimes the bulk of your time goes into cleaning your data at the beginning. And that is a kind of sometimes unfortunately manual thing. And that's important for it to be manual, because when you plot it and you say, okay, I got a sudden jump over here, that's this pump kicking on, ignore this time step or whatever, that's working with operators and others. It starts manual, but obviously that's not scalable. And so there are automated ways to go about this. For me, for like just personally, at least, that's where I like to use machine learning models that have like a statistical stint to them. So error bars and other kind of things. So you were mentioning the regression model earlier. There's Bayesian regression models that give us error bars, and they can account for these things in way different data points over others. But if you start looking online, and actually these days I don't even look online as much as like kind of chat with these models to try to discover these things and code side by side with them, right? Like even if you don't have a background coding, you'd be surprised how quickly you can generate code to run these kind of things. There's a world of algorithms out there that are going to detect sudden changes in your system. They're going to label your data. They're going to detect your outliers. And like it's hard to know which ones are needed until you know what the application kind of looks like. But at least right now, before you go to the expert and ask them, you could chat with an LLM, for example, to see what makes sense. But unfortunately, at least for now, building, at least for us who have limited amounts of data, that manual scan first order pass, as well as like applying some of these outlier detection algorithms is important. What's interesting about models that have terabytes and more data, like when you think about large language models, there's a lot of data on the internet and text that's maybe not correct, but you just take this giant volume of it, and then they also have people who have to figure out how to like label these kind of things. Ultimately, hopefully the weight of those valid readings outweighs the rest. If not, you have to manually check. Like LLMs also, they consume the whole entire internet, but there's that kind of thing of people sitting somewhere and manually labeling data points. It's just impossible to avoid. But once you do that, you can reap the benefits of these kind of things. So
No, they'll still be the community standards police of the social media, right?
yeah.
So was your post acceptable or not?
Yeah.
So
Yeah.
so a specific question we had to come in. Can you talk a little bit about models that are specifically designed to detect anomalies versus models that are specific for optimization?
Right. So when we talk about anomaly detection, like I guess we can talk about like I'll just give two examples and I'm not sure where the question comes from. So we could clarify and say like which domain are you thinking about? But when you think about, you know, there's a data stream in your plant or something like that, and all of a sudden there's a spike. That would be an anomaly, right? In the classic literature of time series or maybe like signal processing, that would be called change point detection. I have an operational point, all of a sudden it's changed, and I want to know when it's changed. There's various things you can do to do this. At the simplest level, you can just have a moving average with a statistical error and say like, oh, this new data point is 2 standard deviations away, something's happened there. That's pretty easy to implement. There's much more complicated models that look at trends and other kind of things. So yes, change point detection and anomaly detection are basically looking at data, determining trends, figuring out if something looks like an outlier, whether it's statistical or some sort of other approach. Optimization algorithms are a little bit different. They oftentimes assume, depending on the algorithm, not all of them, that you have clean data coming in and they're just making a decision. So when that PID controller kicks on or where something more sophisticated like feedback control or even one of these neural controllers get their data, they have to have some assurance that those water levels are correct before they open and close the valve. Now you can build algorithms that have multiple layers in them, but they're two distinct problems. And again, like I know sometimes people ask these questions of how much data do I need? What's a good algorithm? The problem is that that bubble is fairly large and has so many different models in it without trying several of them and without knowing the specific context of the problem. I'm really hesitant sometimes to suggest go follow this track, right? Like there's things that work for me, but ultimately experimenting around is the way to go. But those are two distinct approaches, yeah.
Perfect, perfect. Another specific one that came in, statistical modeling may not always mean cause effect. That can only be deduced from mechanistic or empirical models. I found that kind of interesting way to phrase the question. Can you tell us more about how this actually works? Are we making a mistake by relying more on statistical deductions that AI may rely on? So it's a lot in that question if you want to try to grapple with that.
Yeah, let me see if I understand the question. Maybe you and I can agree on what it's asking. Like when you look at statistical models, there's some rules that determine when something is out of bounds or whatever. And when you're running a mechanistic model, at least you know how the equations that are informing the model should be behaving, and you know that something's an outlier. Um, you can have both. In fact, like one of the things we were looking at is when you have a limited amount of data from your plant and you can't convince the operators, rightfully so, to put the plant through its paces and give you what you're looking for, you could calibrate a mechanistic model around that range, have it generate synthetic data on those outliers, apply some statistics around it. So there's a way to do all of these different things. But for folks that are used to running mechanistic models, you can go back and understand maybe why that happened. Why is it outside of this range? You follow the differential equations and other things, back to the source, the first principles.
Mhm.
Once you get more familiar with machine learning models, you can do similar things, but not to that extent. And for some reason, the way we're trained, we have this feeling of differential equations, for example. We understand how they work, but do we really? It's just that we've seen them sufficiently to understand, because does a process really behave according to a differential equation, or does the differential equation just fit the data? And if the answer is it fits the data, then it's maybe also under this umbrella of machine learning, right? You're fitting these kind of things. And so I'm afraid sometimes there isn't an exact answer to these kind of things, but I think we should also be honest about the fact that you shouldn't be throwing away your current toolbox. Like, we need to understand mechanistic modeling. We need to remember how that stuff works. We're just adding new, we're just adding new tools to it.
Perfect. No, I appreciate that. So, yeah, you probably hear my phone ringing in the
All good, no
background. My
worries.
wife calling me in. So sorry about that.
All good.
All right. So one of the questions that we had here was kind of moving on into this idea of like, the future, right? So some specifics here. So how do you envision training or applying AI for climate change variability on water system modeling, as we don't have much historic extreme data yet? So this kind of goes to that mechanism versus data versus outlier. So
Yeah. Well, that's kind of at the heart of why I think we're building these models, right? We're like, hey, we have a lot of data. That's precisely maybe the example we're giving earlier. We have some data. I don't want to predict what the data measures. Oftentimes I want to predict what was not measured. And that's kind of at the heart of extreme events too, is like we are wanting to predict something that we haven't observed. And that's again going to be at the, discretion of the individual person who's kind of pursuing these kind of things. So like, how we've done it traditionally, like when you look at stream gauges and stuff like that, we fit statistical distributions and we try to take the outliers from the distribution, hoping that those reflect the fitting of the data. But as we're seeing, trends are changing and it's really, really tricky. Personally, that's where I oftentimes then lean into mechanistic models, because I don't, I'm not going to be able to predict those kind of outliers necessarily. So I wish I had like a good example for you of how we did it. Oftentimes, like when we're doing control algorithms, we'll just hit it with a bigger storm, but I'm not necessarily sure that those storms are representative of what we might be seeing in the future. All I know is that, for example, when you do things like feedback control, you're not designing a system to behave the same way every time. So if the regime does change, at least you can change with it. So it's not just adopting in real time, but you're sort of building the tools and the data and the insights to know that the regime is changing and you can adopt your algorithms that way. So at least you don't have to wait another 50 years to rebuild your infrastructure. So, this question comes up a lot. So at least I don't work on this. I don't know how to predict like future rainfall, but lots of other folks are working on it. But we can take those kind of extreme events and put them through these models and see what happens. But at least from my perspective, there is no magical model they can train with current data and expect it to predict the future, unless it's more sophisticated. And I think you can look at some of these like digital earth models that are being run right now, like, tech companies are running them, universities are running them. They are trying to predict these extreme events, and oftentimes they need a lot of computational power. And again, it's maybe outside of the realm of today's examples.
yeah, no, future casting is difficult, whether it's by a person or by a machine or whatever, right?
Right.
There was a similar question that was asking about this, particularly like in arid regions with runoff. But again, it's a similar kind of issue, right? Like, what does a future weather pattern look like given past weather patterns? Yeah, it's a great question, but maybe
Yeah.
not easily solved. So
Yeah, people are working on it, right? Like people are working on it and they're building these kind of models. And especially these digital earth models are pretty impressive, because like you would require traditionally a tremendous amount of solutions to differential equations to do them. And so they then build these sort of like surrogate models using neural networks that allow you to at least get to the answer quicker, right? You can explore those scenarios quicker and then follow the breadcrumbs to where they take you. Again, that's a singular example of something. But there isn't like, I guess, there isn't like one machine learning model to my knowledge that works better for like predicting extremes than others. Again, knowing what the context is oftentimes helps. It depends on what the data look like, what the application is, and then you can kind of select the appropriate model for that application.
So to push a little further, right, to kind of put you on the spot, can you give
Sure.
some names? Like if somebody was going to go Google this or read a little bit more, are there some things they should be reading in this space? Can you give them some breadcrumbs that you'd be like, hey, read, start with this person or start with a couple of these keywords? Are there a few things you can give them that they might be able to then have some breadcrumbs?
So specific to the question of climate adaptation or surrogate
Correct.
modeling or whatever.
Hmm.
I mean, I can tell you sort of what I'm reading these days, right? Like I'm reading a mix of academic papers as well as like staying on top of uh, things like Medium, like blog posts where people are kind of telling you what's going on in the tech industry. So there's specific AI podcasts and other things we can talk about. I really like the work that's being done. There's a lot of good work being done out of the Netherlands. And if you look at like Delft, and again, international, there's lots of folks working on it. But within the area of, let's say, hydroinformatics, they are really considering like how we used to traditionally build mechanistic models, how we build complementary AI models that give us similar answers and faster. And so they have built a really solid group of researchers there that oftentimes keep track of their papers there. So
Okay.
if you look at the work being done at Delft, I personally like it, but again, that's sometimes an opinion or just kind
Yeah.
of on
No,
the.
but that just, I mean, it's just, you're an expert personal opinions are valuable piece of data, right? So,
Sure.
it helps people with breadcrumbs. So now let's now pivot to one that is, we've got a question here from the audience, and then we'll kind of take it to the next step. So the question from the audience is how close are we to being a way to move away from relying on government for environmental measurements and forecasts at scale? Sensors and models are becoming less expensive, more widely available. Organizations like First Street are providing data compilations and model forecasts that government agencies may even be reluctant to do. So in this citizen science and this kind of democracy of science, what are your thoughts between the sensor networks you're working with, this autonomous agents that you're talking about in your example? Where do you see that going? And then, and let's think about this in an equity perspective and what that looks like. Because governments have got certain obligations, and if I can go off and do it as citizen science, well, then I may just be leveraging my position of privilege to begin with to even have more privilege. So let's address the citizen science part first, and then talk about the next step from that. So
Okay, so a bunch of things going on. But basically, so it's
yeah,
saying like traditionally government would collect the data and make decisions and
publish it, and
now we're
right, it would
saying
affect
like
where our roads were, it would affect the value of our homes, all that kind of stuff.
right. And now we're seeing an influx of, or we have seen it, but we're seeing more and more commercial solutions, like third-party providers of data, of tools, and other kind of things that are allowing us to, for example, in the example that you're giving us, see what the floodplain looks like, but I'm not getting it from FEMA, I'm getting it from somebody else, right?
Could be
A
that.
wave of citizen scientists that maybe the barrier to doing these kind of things has traditionally been high and now it's lower. What do we do? And I think that, as you point out, it's a core part of it is at the overall mission. So at least like it seems to me like, and again, this is not my expertise. So I don't do policy, I don't do these kind of things, but like government competes against different interests within its constituency. It has to meet the needs, or it should meet the needs of all the people that live within it. And so they have ways about doing it. And some of these other organizations have other goals, right? Like citizen scientists sometimes have a goal that they want to reach with the argument that they're making. Companies might have underlying things that they're pursuing as well. So again, like I think we have to be able to evaluate these tools and kind of like practically look at what they're providing us and then make a decision, right? Like, are they accurate? If they're accurate, okay, that's another objective source of data. And start like, is it bad that we have competing sources of data? Especially in a time where it's becoming trickier and trickier to scale up the amount of data that's being provided publicly. So you're right, there's the gold standard, like we can look at the USGS, there's the gold standard of stream gauging around the United States, an incredibly impressive network that's taken 100 years to build to provide us with that data. And there's a reason why it's trusted, right? It comes from a neutral party. It has been vetted over the years. It's calibrated. It's all these different things, but it's not available and accessible and affordable by everybody. So then the question becomes, how do you start scaling these networks around these gauges, not to replace them, but maybe to complement them?
Hmm.
And it's hard for me to see that that's a bad thing, because when you're providing physical information on the ground, like water levels or flows, unless there's something fundamentally flawed with it, it seems hard because you're making a physical measurement. I think it provides another source of information. Now, what that means for decision making and, if governments use that data or not, that's again at the local level and they got to kind of sort these things out. So it's hard to say again without a specific example of what we're talking about.
Sure.
Are these things bad or good? I think they just add more people to the conversation, and we just got to look out for the fact that maybe one doesn't overpower the other, that we have a level way to compare these things, that we have ground truth, and I think that's why they're doing benchmarks of LLMs. That's why in some cases they're releasing the open source version. That's what we've been doing for a long time, saying like, look, here's a new way to do it, but here's how all the nuts and bolts of this work. That's why we made OpenStorm open source, with the idea that even if you don't know how it works, you can go online and see how it's put together, and you can come to your own conclusions on if you want to trust it, how it works. Maybe it even lends to this broader discussion about how these things come together and how they operate and should we be adopting them or not. But is it bad or good that these things are being added? It's hard for me to think that it's bad to have more people at the table having the discussion, as long as it's not being dominated entirely and we're missing out completely on a group that's no longer part of the conversation, right?
Okay. No, that's a very fair, yeah. And that wasn't the focus of your presentation, but it
Mhm.
is a good place to kind of have you as an expert weigh in. So along those lines, as we're starting to wrap up, having you as an expert weigh in, right? So we've got seasoned professionals on here, we've got emerging professionals, we've got students. What would be your, kind of words of wisdom to each of those groups when they're dealing with artificial intelligence, large language model, any or all of the above, realizing the nuance that you're not equating them all as the same? What would be your advice to those different bins of people in terms of how they engage with this?
Um, don't snooze on it, right? Don't snooze on it. It's hard to snooze on it when it's the #1 app in the App Store, so at least it's in people's faces, right? But like, technology has been changing over time. One could argue if this next jump is as big as people say. Everybody can have an opinion about that. We don't know until it actually plays out. But like, there's a variant of people who are maybe very seasoned experts who put their expertise into one of these things and say, hey, they gave a pretty good answer, but not nearly as good as I would have given because I know what I'm doing. My answer to those folks would be, don't snooze, because that's as bad as it's ever going to be moving forward.
Right.
Today, when you put it in and that answer didn't meet your needs, it's never going to get worse moving
Right.
forward. So then what do you do with that, right? Because even if it makes stepwise increments over time, those things add up. So it doesn't hurt to have a level of respect for it and make the assumption that it's evolving and doing these kind of things. And it can't hurt to engage with it, or at least learn how to use it for basic day-to-day things, and you can decide if it goes on. I think they're able, just like that example I showed earlier, maybe a baseline LLM can't answer all your questions about civil engineering, but as soon as you connect these agents to the kind of tools that usually only a sophisticated engineer or scientist would know how to do, all of a sudden they're able to answer more and more questions that were typically confined to a professional segment of our population, that they were the only ones who could answer those kind of questions. And as that increases, I think we have to be thinking about like what the role of expertise is, what the role of like engaging with these things is, and what that means for like, if you now can produce an answer to a question in a minute, whereas opposed before it took like weeks of setting all these things up and running them, what does that mean for the rest of your time? What does that mean for the size of your team? We still don't know how the trends are shaking out in the job sector, but you just read the news and you can see opinions. So, anything could happen as far as, things are going right now. And then as for the students, I think that the educational sphere is still adopting to all these things. We're trying to figure out what this means for the classroom. It's our discussion
Sure.
earlier, like, do we flip the classroom? Do we still talk at the whiteboard and hope that the classic way of delivering content is really what people need, because content is at their fingertips? I think students are wise enough to know that society is changing very quickly, sometimes maybe changing a little bit quicker than a curriculum can adapt. So that's on us as educators to try to figure out how to stay on top of it. Like, my policy in my class is, you're encouraged to use it, you should be using it. It's on me to figure out how to engage you and make sure that you're still working hard in this class and all these other things. But even if you're not predisposed to be a coder or programmer or any of these other kind of things, maintain curiosity in these tools as a student. It won't hurt you if you're somebody who knows how to use these tools beyond just kind of prompting them for one answer. So connecting them to tools and other kind of things. And so work outside the classroom, try these tools, listen to podcasts, figure out what's going on. And that might prepare you later on when people are considering for hiring and other things, at least to have that extra thing to know that, how you're using these things. You can pitch that to prospective employers. So just, summarizing it, don't snooze on it. It doesn't seem, at least compared to 10 years ago, that it was like, oh, this is cool, let's see how it shakes out. This is cool and moving fairly quickly. Again, that's an opinion. We don't know exactly how it's all going to shake out. But at least in my daily workflows, I use it all the time.
Dr. Kirkes, thank you so much. This has been so informative. We are incredibly grateful for you spending some time with us today, and we will turn it back over to Marissa for wrapping up.
Okay, thanks, Dan, and Thank you, everyone, for all your questions, and thank you to our speaker for sharing your knowledge with us today. We have several webinars planned in the near future. You can go to aaes.org/events and reserve your spot. Just a reminder, if you're not yet a member and you're considering joining the Academy, you can email me to discuss our membership options. For all board certified individuals, PDH certificates for this event will be sent out by the end of the week. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day.